Okay, Year 11, I'm going to go through the next unit, which is logarithms. Now, I'm just going to go back a bit before I introduce you to logarithms. I'm going to go back to when you were in Year 8 and you'd never seen, and you're learning about Pythagoras for the first time, and you get this equation where you go, x squared equals 16, and all of a sudden your maths teacher said, well, we need to find a number. We need to find a number that multiplies by itself to give 16. And everyone puts up their hand and says 4. And all of a sudden you would have been introduced to this symbol, this radical symbol. And you're going, oh, what's that? What's that? And when you're in Year 8 and you've never seen it before, it's something new, it's something different. But by the time you're in Year 11, you understand what that is. And you know that it's going to give you plus or minus 4. And that is, well, you would call it a square root, but it's a radical. It's only a square root because you're using the power of 2. For example, if you'd been told that the cube, x cubed equals 8, well, then you have to do the cube root of 8, and you're going to get 2. All right? So there's a symbol. It's an undoing. We call it an inverse operation, and every operation in mathematics has an inverse operation. And to help us with that, like if we were to graph that, if we were to graph y equals x squared, so here we go, I'll graph y equals x squared, and we know that y equals x squared looks like this. There it is, y equals x squared. And then if I were to graph the square root, so y equals plus or minus the square root of x, I get something like that, which can also be written as x equals y squared if I square both sides of that equation. Anyway, they're two inverse operators. And the really cool thing about inverse operators is that they are a reflection in the line y equals x. So let's take the graphs that we know. So we'll draw another little set of axes here. And if we draw y equals a to the x, and we get that one, going through 1, that's y equals a to the x. Well, the thing that undoes it, the inverse operator, will be a reflection there, going through 1. And we call this, or this operator is y equals log to the base a x, and they are the inverse operator because they are a reflection in the line y equals x. So let's now have a look at our definition. And our definition is here. I've circled it with the highlighted pink. And if y equals a to the x, then x, the undoing, is to take the log base a of y. And this is what I want you to write in your notes. This bit here. This is the basis. And we're going to be moving in and out of both these operators. So if I gave you 2 to the power of 3 equals 8, 2 to the power of 3 equals 8, okay, actually I'll write that as in the set to make it even easier. So 8 equals 2 to the power of 3. Well, the 3 is where the x is, so 3. The 8 is where the y is, and the 2 is where the a is. So 3 equals log to the base 2 of 8. All right, because that's your x. That's your x. That's your x. That's your a, and that's your y, and you can see where they all end up. And you've got to be able to move in and out of that. This whole exercise is about doing that. But there are some other laws too. So the first one here, so as you can see here, I've drawn y equals a to the x and x equals log to the base a y. And we take this one here, which is log a of a equals 1. Well, why is that true? Why is the log of any number when its base and the number are the same equal to 1? Well, let's just go, well, what is? Let's take x equals log a to the a. Now you can see here we're going to work backwards. I've drawn the green arrow. So what goes where? So this x goes up into the power. So when I solve this, I'm going to get a equals a to the x. Now, what value is that going to be to make that true? A equals, because there's a 1 there, there's a 1 there, even though it's not there. A to the 1 equals, so x equals 1. So therefore, log of it. So there's your first law. All right. Now, what about log a to the 1? So let's take that. And again, we can just use this law, log a to the 1. Okay, well, they're telling us that it equals 0. So let's go, x equals log a to the 1. Okay, so again, we change this around using this identity up here, using our identity. We're going to go backwards, and you're going to have to see what's what. And that means 1 equals a to the x. Now remember, a is a number, and what power of x is going to let that be true? Well, you should know that x is going to have to equal 0. So therefore, we've got this one. So there's our second one. Now, the next one. It's a little bit trickier. So let's have a look at it. But again, we're going to use the same law. So we've got log a to the x. Okay, well, let's call it something. We'll use a variable. I'll just pick another variable. We'll go, we'll let m equal that. And they're saying that equals x. Let me get rid of that. Saying that that's what well, let's prove it. That equals x. Now, how do we prove that? Well, let's just rearrange this whole thing. Let's rearrange this whole thing and go back. So I've got that log, and imagine, and let's say write it like that, x equals log a to the x. Let's write it like that. So it makes it easy to go backwards. So we're going from the bottom to the top. So that means, okay, well, that is my y. So because it corresponds with that bit there. So I'm going to get a to the x, because I'm going back, a to the x equals, okay, this is going to be up there, so it's going to be and equals a to the x. All right. So I've just gone backwards, so that's true. Okay, well, that's cool. Now the last one, I don't tend to use the last one a lot. A to the log ax equals x. So log ax. Sorry. A log ax equals x. All right, so now if I'm going to go this way this time. I'm going to go this way. So that's going to give me what happens there. I've got, and if I wrote it the other way, it might make it easier. So I'll write x equals a log ax. So it's in the same order. And we're mirroring this. So that's your y. That's your y when we come down. And all of this is your x. So I've got, okay. So that's going to become log a to the x equals log, a to the x. Oh, that's true. That's true if I follow that. So there's your next one. And then there's one more, there's one more that I want to do for you. There's one more that I want to do for you. And it's this one, which is log ax to the n. And we're going to go, that equals n log a to the x. So if you've got a power in there, if you've got that power in there, it can just plop out the front. Now, how does that work? How does that work? So what I get is I go, I'm going to let x equal a to the m. Therefore, m equals log a to the x. Right? And I can say that. I can say that x can be represented by any number, a particular number to a power. It can. So if I then go, x to the n, well, that equals a m to the n. And we know by our index laws that we multiply those and we get a to the mn. Now, if I now go, and that's what x to the n is. If I now use change of base, I'd use that law, not this one here. If I use my identity, that means that mn equals log a x to the n. Now, mn, well, m is log ax. So I can say that log, because over here I did, that's what m is, so I'll put that in for m, and I get log a x, and I've got an n. And just to make it nice and neat, so I'm going to pull that n out the front, and I'm going to get n log base ax equals log ax to the n, which is the one that we need. So I'm going to hold the video there, and I'm going to make another video of the questions, but I just wanted to go through those proofs.